The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
I would like to acknowledge Eric, and he was at Universidad Autónoma de Yucatán in Mérida, Mexico. That's my alma mater for my bachelor's degree. Briefly, most of what we are going to talk today is experimental with a little bit of the modeling that we continue to do. And Eric will be this. And also would like to acknowledge most of the research. It was sponsored by the Florida Department of Transportation, and although several years we did it kind of pro bono, it's a study that spans 21 years by now. Some of you have had here mentioned that Florida does worry about chlorides. We have a good number of bridges that are either exposed in the ocean or on the Gulf side or in brackish water. Since maybe the late 1980s, FDOT started using silica fume and fly ash as cementitious admixtures to reduce the chloride penetration. In this particular study, we are going to be talking about binary mixes. So we look either at the fly ash effect or the silica fume effect in different amounts. And we did the test in fresh seawater, outdoor exposure in South Florida. Also, something that has been reported is that there is a good correlation between chloride diffusivity and resistivity from laboratory measurements. Going directly into the type of mixes, there were two mixes that are identified here as AO and CO that contain no fly ash or silica fume, but the CO did contain calcium nitride. And then there were four mixes that were prepared with 20, 35%, 50%, and the 35% with nitrite. And the way that we calculate percent of fly ash is by using this formula, the amount of fly ash divided by the total cement plus fly ash, and the silica fume similarly divided by cement plus silica fume. And a note, by looking at the numbers, I was trying to figure out why the percent of silica fume was so large. Turns out that in this particular study, and actually started long before I joined FAU, they use silica fume in a slurry form, okay? And that is going to become a little more clear here, where a fraction of the mass was used towards the water. You can see here the amount of water is significantly smaller. And this is a very busy tables that are in here, but hopefully you get access to the SP when it's published, and you can then take a look at this. The main points that I want to make in here is that the range of the unit weight in kilograms per meter cube of the concrete range between 20 to 30, and in some cases, the ones with fly ash went to 2280 kilograms per meter cube. And the other point that I want to mention is that the target cementitious material for all mixes was of the order of 400 kilograms per meter cube, okay? So when, in my presentation later on, I use the amounts of chlorides in kilograms per meter cube, to keep in mind that the cementitious that was used per unit weight is 400. To make your back of the envelope calculations. We actually use in some of our computations the values that are displayed in this screen. And the other thing that I forgot to mention probably is that the type of fly ash that was used is type F fly ash. So this is the type of specimens. They contain 5 rebars of 0.95 centimeters in diameter. And there were a large number of specimens that were prepared for each one of the mixes. And some of them were 12.5 centimeters in height, others were 15.2 centimeters. And the one with 12.5 contained concrete cover of 1.9 centimeters, and the ones with higher, they contain 3.2 centimeters in concrete cover. And we'll see why that might become relevant in a little bit. Actually, something that is important to mention, although you see right now that these 3 rebars are at the top, when they were cast, they were at the bottom. So they were flipped before we placed the polycarbonate. And this actually took place, the samples were prepared in 1994 during the fall. Actually, incidentally, that's the summer that I came to the US to start my PhD studies. And then they were transferred to Florida Atlantic University in early 1995. And since then, they have been exposed to fresh seawater 1 week with and 1 week without. Additionally, since you can see from the picture, you can see some of the greenery there. They are exposed outdoors, so they are also exposed to the temperature and humidity changes that might be taking place during that time. So by now, we have 7,600 days, so close to 21 years of exposure. Some of the measurements that were performed, potential versus time of each one of the rebars, I forgot to mention 2 pairs in here. There were actually 5 rebars, and 2 pairs were interconnected, whereas the middle one was not. And then we terminated specimens at 5,700 days, 6,000, and 6,200 days. And the instance of 5,700 days, we terminated 1 specimen per type of mix. Then, in addition to that, the cuts longitudinal, you'll see in just a moment what I mean by that, and we exposed the rebars, and we took part of the concrete above the rebar, and most instances there was corrosion. So on the sections that there was no corrosion, we did some milling, and we obtained concrete powder so that then we can calculate what was the chloride concentration right at the rebar trace. In addition, before we did actually the cutting, we obtained concrete cores so that we can characterize the chloride profiles as a function of depth and also the resistivity of the specimens. So this is one of those specimens, and incidentally, 5,600 days, this was the only one that actually showed some cracks, and is the one that contained only OPC. So this is the coring that you can see here. These are the initial cuts. Then there were 2 additional cuts that were done in this direction along the depth of the rebar from both sides without touching the rebar. Then we chisel it up and we expose the rebars, and you'll see how that looks in just a moment. In addition, on those cores, we perform resistivity versus time, and we increase the moisture until the values were stable. And then, as I mentioned earlier, we obtain chloride profiles from those cores, and from those profiles, then we estimated the apparent diffusivity. And the resistivity was measured by the Wenner probe approach following FDOT FM 78. Although that particular specification, we didn't modify because that our cores, as you remember, I mentioned, were either 12.5 or 15 centimeters in height, and this specification called for a 3.8 centimeter spacing. You cannot do it. So fortunately, we were using this type of probes where you can adjust the spacing, and we did it either with 2 or 2.5 centimeter spacing. And there is a correction that needs to be done. The values that the BICE reports are assuming that you have an infinite amount of concrete. That's not the case in the small core. So in here, you can see the calculations, and actually, this is something that was reported before by Morris, Moreno, and Sagüez. But we did our own calculations, and we did apply the cell constants correction, and the values that you'll see later have that included in them. With respect with the slicing to get the chloride profiles, we sliced them in sections of 0.25 inches or 0.635 centimeters each. They were pulverized and then using FDOT method, that is an acid-soluble method to obtain the total amount of chlorides. So very briefly, talking a little bit about some of the typical potentials, and one of the first speakers mentioned that over time there is a potential decay, and indeed, in this case, it's kind of a mix because the samples were outdoors, so there is a field part of it, although the specimens were prepared in the lab. And you can see that even after 2,000 days, there is still a decay that is taking place. Eventually, close to 4,500 days, there was a decay, so maybe some more pitting took place, but then it recovered. And in this particular case, we terminated the specimens at 5,700 days at a potential of minus 100. And I apologize, the values in here are versus calomel. So if you want to figure out what is the value versus copper sulfate, the 200 value is about 120 versus calomel, and the 350 will be like 270 versus calomel. Okay? Incidentally, most of other research that we have done in the lab versus calomel, if you reach between minus 180 and 200, it's likely that corrosion has initiated. So this is somewhere in between the typical minus 200 and minus 350 that is usually reported. And in this other sample, you can see that the 3 rebars activated, and these 2 corresponds for the ones that had the 1.9 centimeters concrete cover, whereas this one here on the bottom corresponds to one of the specimens that contain 3.2 concrete covers. So let me skip some of this. And again, this you will be able to see it on the paper. So just to demonstrate that indeed each one of the rebars initiated corrosion. So you can see that this is the actual rebar, and this is the rebar trace. So these are the sections that were milled to obtain the concrete powder to calculate the amount of concrete at the rebar trace. And this is the amount, the chloride profiles. Something that I want to mention is that these values that you see in these circles corresponds to those values that were obtained on the rebar trace. You can see that they are larger than what you have predicted from the profiles. And this we have reported with Dr. Kranz and Dr. Sagüez before, that indeed the presence of the rebar can increase the amount of concentration that is accumulated on top of the rebar. And this is more relevant as the ratio between the concrete cover and the radius of the rebar that is used. If that is smaller, that might be more important. I'm not going to go into this table. I want to show you a little bit about this other table. And what we found is that the amount, and I'm going to refer, the values are reported in two manners, in kilograms per meter cube and also in percent cementitious. And I think that this might be a little more interesting. I forgot to mention the previous slides. They were on the right, we have the values in percent cementitious, on the left in kilograms per meter cube. These are for OPC, fly ash, and silica fume. And what we found is that the values for those in fly ash, if we took and verified that corrosion indeed took place, and only considering those where corrosion was verified, then we either found the minimum value or the average value. So you can see that for the OPC varies between 1.45 was the minimum, whereas the average was 1.92. Interestingly, for fly ash, if you look just at the minimum, it went from 0.75 to 1.3 to 0.29. If you look at the average, that range is between 1, 1.3, and 0.5. For that contained both fly ash and the calcium nitrate, the values were a little bit higher, but then again, it reached this concentration in the same amount of time, approximately. For those with silica fume, the values that we observed that for the minimum were a little bit larger, 1.8, 1.5, and 0.6. And interestingly, in this case, the one that contained silica fume at this level of 15% and nitrate didn't initiate corrosion, so the minimum was greater than 1.46. And we have here the diffusivity versus resistivity. And the diffusivity was measured after 3.3 years and also after the amount greater than 15.5 years. And you can see that indeed, as other have reported, the diffusivity decreases as time progresses in this case. The other thing, this is not something that I did, but since our previous speaker mentioned that the pH might be one of the important factors, you can see in here that indeed, as you increase the amount of fly ash, the pH decreases. So that might partially explain why the amount of chlorides that allow corrosion to initiate was different. And similar calculations that include the one-dimensional diffusion and the presence of the rebar. And then we took the values from the diffusivity and the surface concentration that was measured, and including, this is from the paper with Dr. Kranz and Dr. Sagüez for the deaerating factor and the rebar presence. And then what we did is, what happens if you have then 5 centimeter concrete cover and a 7.5 centimeter concrete cover, rather than the dimensions that I had mentioned before. And we found that in that case, then the OPC will have taken 25.9 years before corrosion initiated, and if you have a 3-inch concrete cover, close to 65. Whereas for the fly ash, there was almost no difference between them once that you account for the different chloride threshold, again, for the level that caused a certain amount of corrosion. And in here, there was then 90 years before corrosion initiated and about 210 for the 20% fly ash and 200 for 50% when you have 3 inches concrete cover. And then we validated the measurements that we obtained, and we found that if you use the deaerating factor directly, we, in some cases, predicted a larger number of years, and in others, a smaller for the case of the OPC. And the reason for that is that the concrete, in addition to that, is heterogeneous, so that was not considered, and also exposing it to seawater, there might be some calcareous deposit that might start forming in there that might also modify at the initial layer how the chlorides are transported. So thank you for your attention, and this is the ugly place that I have to go every day to work.
The previous speaker said something to the effect that the addition of fly ash would raise the internal chlorides potentially over the ASTM standard?
No, it doesn't raise it. It just, the calculated values will be higher on the base of cement.
The calculated values, so it wouldn't exceed those standards? No. Okay, and that answers my question. Thank you.